Right, our last talk of the day is Michael Hrušák of Mexico, who will talk about long and short recursive constructions.
Thank you very much. First of all, I would like to thank the organizers, of whom I see at least one, for having me, for inviting me here, and for giving me the opportunity to talk to you. I have recently heard from a colleague of ours sort of a criticism of the field of cardinal invariants, that all you do with cardinal invariants is to prove that they are consistently different. And so I would like to convince you that there is actually a lot more to cardinal invariants and related things than that. So talking about cardinal invariants, there is a nice definition that I stole from Andreas. So take your favorite theorem which holds for all f0 and look for the first kappa where it fails. It's typically a cardinal invariant. An example is, and I will stick with that because I don't want to give, at least not at the beginning, too many technical definitions. So I will work with the bounding number. That means what is the underlying theorem for all f0? If you take countably many functions from omega to omega, you can find another function which is not bounded by any of the countably many. So according to the template, B is the minimal cardinal where that fails. That means the minimal size of a family which is unbounded. What did I say? I said bounded. I should have said bounded, but that's right. The definition is correct. Now,
excuse me, the cardinal characteristic is a much better name than invariant, because it's only one thing. So
I agree. And so what we do with cardinal invariants is we compare them. We create a maze of these relations. So an arrow from a cardinal invariant to another cardinal invariant means that where the arrow starts is smaller than where it ends. And I think most of you have already seen this picture, and there are other pictures to work with. And typically when there is not an arrow, then it actually means that they are consistently different. Now, the main thing that I will be talking about is the short iterations, and that means corresponding parametrized diamond principles, which are modeled on this Devlin-Shella weak diamond. So let's take a look at that. What does the weak diamond principle say? If you sort of ignore the first quantifier, it has the structure of a diamond sequence. So it says there is a diamond sequence which stationarily often guesses something, right? But there is this extra quantifier, so it's sort of diamond with preparation. And it sort of works like writing a grant proposal, if you think about it. This function typically tells you how to construct a thing if you already get the funding, if you get what you want, if you get the diamond sequence. And at the end, once you wrote your proposal, you got your grant, you just show that you can actually do everything you promised that you would do. And that's what the last part of the statement does. Now, it's rather a remarkable fact that this non-trivial guessing principle is actually not a guessing principle. It's just a cardinal arithmetic assumption. But that changes dramatically if one makes even slight alteration to this definition. So I was hoping Mirna would be here because this talk was mainly sort of intended to be a gift to her birthday, but well, will not do. Anyway, so I'll give you an example of one of these parametrized diamond principles, and I will take this cardinal B as a base for it, or as the parameter. So there are several changes. The overall structure is the same as for this Devlin-Cella diamond, but there are the several changes pointed out. So first of all, what did that statement say? Actually, I didn't. Let me return to that. Say. So what are we saying? So we are coloring the nodes of a complete binary tree of height omega 1 here by 2 colors. And for each such coloring, we are saying there is a guessing sequence. That means along every branch of the tree, we have guessed the color stationarily often. Okay? So this is the same thing that we will be doing later on. So we have, again, a coloring of the complete binary tree of height omega 1 here by a different set of colors. Here the colors are functions from omega to omega. And a guessing sequence, again, gives us an omega 1 sequence of these functions. And what we want, again, along every branch of the tree, we guess stationarily often, but here guessing is relaxed. We don't have to guess exactly. We just have this relation which tells us when G alpha guesses the color of the restriction of F. Okay? And for sort of technical reasons or utility reasons, we require that the coloring is nice. And by nice, at least initially, we mean that it's Borel on levels. So for every alpha, we can think of 2 to the alpha as a copy of the Cantor space, and we just require that the restriction of that coloring to that level is a Borel function. So what's the sort of the main point about this is that in nice iterations, countable support iterations of a fixed definable partial order, if the cardinal invariant is small, then actually the corresponding diamond holds. In our case, we are just looking at the bounding number, so we look at B. So the resulting models are all these models that have names. The Sachs model, Miller model, Blas-Cella model, all these models are of this particular type. So as you know, typically many problems in topologies. Oh, by the way, so I'm here representing topology, I guess co-representing with István. So I will be looking for the source of examples mostly from set theoretic topology. So there are many topological problems which can be solved either by the scale of forcing axioms, let's say by Martin's maximum, or by the axiom of constructibility, or by both. Meaning, axiom of constructibility gives me one answer, forcing axiom gives me another answer, and my problem is undecidable. So that's the kind of problems we are not interested in today. We are interested in problems which are of sort of the form which are, for which perhaps constructibility and forcing axioms do give me answer, but they give me the same answer. So, but not sufficiently. So I want to analyze the problem further. So either, usually in the hope of proving the right model to prove a consistency result. But that new model, I have to look for it. I don't have sort of prepared models, and I need to do some analysis. So a typical model is there a topological space which has some peculiar property, right? Or is there a family of topological spaces, or is there some combinatorial question? So typically an answer to my question or some progress to that question goes like this. First, we find that CH is good enough. we can construct our things assuming CH. Then we see that actually we don't need CH. Martin's axiom is enough. Well, okay, then we work some more, and we actually isolate a cardinal invariant which is responsible for that construction. That means really we need only a fragment of Martin's axiom which says if the cardinal invariant is equal to C, then we can construct the space. So that's what I would refer to as these long recursive constructions. That means I'm doing typically a recursive construction of length continuum, taking care of some requirements one by one. So in C many steps, I fulfill C many promises. Now, I won't be talking about these long things, but the new thing, which I find very interesting, is that there seems to be, to many of these constructions, there seems to be a short companion, meaning usually almost the same idea or very similar idea for construction of my object that I want can be done in omega 1 many steps. So I fulfill C many tasks because I still have the same many tasks as I had before when I wanted to do my long iteration, but now I have only omega 1 many steps to do it in. So it's not surprising that you would need something like a diamond, where the number of tasks is longer than the number of steps you have. You need to guess, and you need to guess correctly, right? So, and all of this is done to either split the problem that I'm interested in into manageable pieces so that I can solve it in each case, and hopefully together it will give me a ZFC answer to the problem I have, or it will give me a limitations on the model that I'm looking for in order to prove the consistency result. And actually both of those happen. So I guess here I want to defend the cardinal invariants. So the way I see cardinal invariants are primarily as a scale against we can gauge these recursive constructions, which can help us to measure sort of in sort of a vague analogy with the consistency strength of large cardinals. We can measure the strength of these principles that we are interested in on this level of combinatorics of the reals. So I would like to give you examples, but I will give you examples which are still open. So I will give you sort of partial progress towards open questions because I also want to do publicity to these problems, which I think are really beautiful problems. So the first one is an old problem of Archangelsky and Franklin, which deals with compact sequential spaces. Okay, so remember that a topological space, for me, unlike for Istvan, all topological spaces are completely regular. So don't come with an answer, I found a Hausdorff space, which satisfies something. I'm not going to be terribly interested in that. So a topological space is sequential if its topology is determined by convergent sequences. And what does that mean in this case? So here is my space. I have a set A, which is not closed. So that means there is a point X, which is in the closure, but not in A. And so fresh A would tell me I can converge to that point. So what does sequential say? It just says, well, there is such a point. So there is a sequence in A which converges to some point outside of A. Right? In other words, if I take all the limits of the points and I iterate, I get the closure of the set. Okay? So the sequential order is simply the ordinal, which tells me how many times I have to iterate in order to get to the closure. Now, this question of Archangelski-Franklin is, well, I guess I should first give you an example. So if you have a MAT family, maximal almost disjoint family, then you can construct or easily describe what's known an Isbell-Mruvka space, which is a space which has scattered space with two levels, omega. The second level is a lot bigger, that's the MAT family. And now the points down here are isolated. Now every point here is also a subset here. And this subset is a convergent sequence to this. So this is a nice separable locally compact space, so it has a one-point compactification. Now, this one-point compactification is a sequential space, and it has sequential order 2. In order to get from omega to infinity, I have to take limits of convergent sequences twice. The first limits appear up here, and now any sequence converges to infinity here. All right, so there are compact spaces of sequential order 2. It is amazing that in ZFC this is all we can do. So the question is, can we get to 3?
Is it consistent in the whole?
It's consistent, as pointed out here, and it's an old result of Bashkirov, that assuming the continuum hypothesis, you can go as far as possible. So there is actually a compact sequential space of sequential order omega 1, or any alpha below omega 1. Now, L and Dow, a few years back, got to 4 with a lot of work, assuming B equals C. And now, it turns out that using this parametrized diamond, you can sort of mimic this construction of Bashkirov and construct. So his space, of course, has size continuum. Our space here has size omega 1, but has the same important properties. So it's this here is the long recursive construction. Here is the short one. But the problem as such is still open. So these are only partial results. So now a more combinatorial question. Yuri Steprans, when did he do that? Sometime in the 80s, I think. He asked the question whether one in ZFC can construct a Cohen indestructible MAT family. It was first proved by Kunin that you can do it assuming CH. We then, with Salvador Garcia, we've isolated B as sort of the natural cardinal invariant for that construction. So there is a Cohen indestructible MAT family assuming B equals C. And again, recently, we've seen again that this construction, long one, has a short analog. So one more problem of Archangelski. This one is directed to Istvan. I think he likes this one. So everybody knows what it means for a topological space to be first countable. That means every point has a countable basis, the countable decreasing basis of neighborhoods, and so of open neighborhoods. So what if we just drop the neighborhood? So that's Archangelski's notion of being weakly first countable is that to any points you can assign, I guess, a decreasing sequence of supersets of X, so sets which contain X as an element, and which determine the topology in the way that the usual neighborhoods would. So a set is open if and only if for every point the set contains one of these pseudo neighborhoods. And The fascinating problem is whether compact, weakly first countable spaces are actually first countable. Again, a long time ago, Yakovlev, assuming CH, constructed a counterexample. And actually, he constructed a counterexample of a particular type where there is exactly one point where the space is not first countable, and the point is sort of an infinity of scattered levels. So again, it's a scattered space. So one can sort of extract the combinatorial feature of that construction, and let's call it a Yakovlev space, even though I'm not going to tell you what it is. And a few years ago, Istvan with Uri Abraham and Isaac Gorelik proved that, again, B equals C gives a construction, actually. Again, it's sort of optimizing the original construction of Yakovlev. There is this Yakovlev space, and again, it turns out that you can do this short iteration to construct space with the same properties. So all of these things in particular show that there are these spaces in models where it was formerly not known whether such spaces exist. So these are sort of somewhat valuable observations, I think. And I guess I'll give you one more example, and that's again an old problem of Scarborough and Stone, whether any product of sequentially compact spaces is countably compact. Again, it's an open problem, and Jerry Vaughan, using Diamond and using a construction of Ostashevsky's, proved that there is a family of counterexamples. Eric van Douwen did the same, assuming B equals C, and again recently we found a parametrized diamond which gives a short iteration. But notice this is sort of asymmetrical. From what I've been giving you so far, you would think that there is a sort of an immediate translation using the same cardinal invariant, because it was always B equals C proved something, diamond B proved the same thing. Well, here it's actually a parametrized principle associated to a different cardinal invariant, and I guess I'll give you now the general definition. So,
excuse me, how many? What is in your result? What is the number of sequentially compact spaces?
2 to omega
1 or
2 to omega 1.
2 to the omega 1.
Yeah. No, really it's 2 to 2. Well, I guess it depends on the size of continuum, 2 to the C. Because for every ultrafilter you construct a space. Anyway, so now let's take a look at sort of a general notion of a characteristic or an invariant. So first I see an invariant as a triple or as a sort of a bipartite graph. So I have two sets A and B, and I have some arrows between A and B. And what are the way I think of it, is that if I take an element of A, then there is some B here which dominates A. So there is an arrow going from A to B. So that's the non-triviality condition 1. And there is another non-triviality condition which says that no B dominates everything. So I need at least two points inside of B. Okay? So that's just a non-triviality condition. And if I have this invariant, then I can assign to it a cardinal invariant, or its evaluation, which just says what is the minimal subfamily over here, such that for everybody here I'll find somebody in that family which dominates it. Okay? So many standard cardinal invariants can be expressed in this form. And for each one of these triples, I have a diamond. Right? So what do I do? Again, I color the complete binary tree by elements of A, and my guessing sequence is a sequence of elements of B. Sorry?
Should that be Borel as before?
Not quite, not yet, but it will be on the next slide. So that's why it's phi. It's not a diamond yet. So, yes, so I'm coloring by A, guessing B's, and the guessing is what you would guess guessing B. That means along every branch, I have guessed according to this relation stationarily often. Okay? Well, so this is a perfectly good combinatorial principle. It has, to our liking, the disadvantage that it implies that 2 to omega is less than 2 to omega 1, because it in particular implies this weak diamond and Devlin and Shella. And since most of the models we are interested in don't have this, don't satisfy this, it's too limiting. So that's why we require exactly that the coloring be Borel again. Okay?
For that you need some topology.
For that you need exactly that A, B, and the relation are definable subsets of some Polish space, which they typically are. Yes?
To have large cardinal, could you put universally bare, or in the place of Borel, could you put universally?
I'll get there. Well, I think I'll get there. And now, so what are sort of the main points? Well, this diamond, of course, implies that the evaluation is at most omega 1, because the range of any G for basically for any reasonable F will give you the cardinal invariant. Diamond, the full diamond is actually equivalent to one of these diamonds. And again, you get a structure against which you can gauge the use of these parametrized diamonds, and that's not quite just comparing the cardinal invariants, but it's Galois key. But it essentially just says, is there a Borel reason why one cardinal invariant is, say, bigger than another cardinal invariant? Just the numbers are not good enough, just having a proof of the numbers. But it's a very similar picture. For instance, for the Chichon diagrams, all the arrows are witnessed by these Galois keys, so there we are safe. Okay? So there the thing is the same. Now, as I told you before, in all these models which have names, so I will call them canonical models, the fact that the evaluation of the invariant is small actually is equivalent to the diamond holding. So these things are very frequent. They all very often hold these parametrized diamond principles. And all right, so a canonical model is a model where you just grab one definable forcing, which is just slightly homogeneous, and you iterate it omega too many times, right? Now, in this original paper, which was done almost 15 years ago, we first look at the standard constructions of diamond and see how we optimize. Just like with cardinal invariants, if I know that Martin's axiom proves something, then I looked for the cardinal invariant which is responsible for that. So now I'm doing the same thing but for diamonds. So I look at a diamond construction and I try to find a cardinal invariant which is responsible for the construction. And in great many cases you can do that. Another sort of main point of that paper was that in the realm of cardinal invariants, there are those which are not of the type that I just wrote. For instance, the almost disjointedness number, the ultra-filter number, independence number. And it turns out that to each of those, so far at least, we can find their sort of Borel brothers. So
what is the S omega?
it's just a version of S. It's not worth. It's S plus epsilon. We don't actually we cannot separate it from it, so it might as well be S. And the other result that's contained in there, that these diamonds are real diamonds. They are guessing principles. They are not just consequence of CH. And of course, unlike the weak diamond of Devlin and Shella, right? And then many people followed afterwards. Yorioka very quickly gave sort of optimized the diamond construction of the CCC destructible gap. Hiroaki Minami showed that even assuming CH, the guessing principles in the Chichon diagrams are different guessing principles. So it's not just that you have this guessing and you tag on a cardinal invariant. They have different strength, even in the presence of CH, these things. And Heike Mildenberger and Saharon looked at, on the previous slide we showed that diamond of the uniformity of the meager ideal gives a Suslin tree. So they show that you can't improve that it's essentially optimal. At least you cannot replace this diamond by any of the other in the Chichon diagram. And very recently we've started looking at these constructions more and more in the optics that I just gave you, that sort of looking at the long recursive constructions and trying to find their short analogues. And in many cases you can do that, and it actually is helpful because, for instance, you want to prove that something is true in the Miller model or in the Sachs model. Normally you would you would have to construct an object using CH, which by hand you would prove indestructible by all these iterations of your forcing, and it gets rather messy. Here you can just, you know that you have these diamonds for free, and they save you from proving all these preservation theorems. So I'm not going to read all of these, but hopefully there is something interesting for every one of you, or at least some of you. So these, of course, again, these are some tailor-made variants on the reaping number. So where am I going to? Oh, okay. So now I'm coming to your question. So actually, when we were writing the original paper with Justin and Mirna, we were debating whether to use Borel, because we were well aware of the fact that for the proofs that these diamonds hold in all these models, we need a lot less than Borel. We just need to know how to interpret things, right? So, but in all the applications, Borel was good enough. So we settled for Borel. But it turns out that we now have applications where Borel is not enough. So I will give you sort of two reasons for that. They're doing all right. So I will replace Borel by something which is formally uglier, but it's really not that bad either. So you just want that this function f, this coloring, is defined using a sequence of Aleph-1 many reals as a parameter. Okay. So now this diamond with this omega 1 pointed out here is the same statement, only I replace Borel colorings by these omega 1 definable colorings. Okay. All right, so I want to give you a quick example of how to use. So even going back to this Devlin and Shella, which is just, we use 2 and equal, right? So the phi of Devlin and Shella is this same statement here, but without any requirements on the definability. If you put this requirement on the definability, then it's not only a consequence of 2 to the omega less than 2 to the omega 1, but also it holds in all of these canonical models. And even though it seems like a very weak principle, it is actually more powerful than you would think. It can do a lot of things. So I want to give you a quick example of how these diamonds work. So for instance, we will use that we will prove that this diamond shows the failure of Baumgartner's theorem. Okay? So Baumgartner's theorem states that all Aleph-1 dense sets of reals are order isomorphic, and it's a consequence of PFA. And this very weak diamond tells us that it's strongly not true. Okay? So in particular, for any Aleph-1 dense set of reals, there is an Aleph-1 dense subset of X such that X and Y are not order isomorphic. And what am I going to do? Well, I need to fulfill C many tasks in omega 1 many steps. So in omega 1 many steps, I want to pick an Aleph-1 dense subset of X, given any X, such that for any homeomorphism, there are C many of those, one point which is in will go out, or one point which is out will go in. That means it kills a homeomorphism. And this is easily done, and it can be done in these 4 lines, but I think I'll skip the proof. But it's quite obvious, here, that in order to prove this, I need the set X as a parameter to define my coloring, right? Well, the set X is a sequence of Aleph-1 many reals. So this is an example, that's sort of a trivial example, that this omega 1 definable is a useful and stronger requirement. And there is another reason. So even if we are looking at these definable cardinal invariants, these Borel cardinal invariants, as I said, just knowing the number is not good enough. You need a good triple for it. And in some of these constructions, you want to use more than one of these cardinal invariants. So you can use a product or something, but very often what you need is this sequential composition. If you think about it, what is a sequential composition of the invariants? All right, so I have 2 invariants. I have triple AB and its arrow, and A prime B prime and its arrow. And what do? I want to say, first I use I, and then I use J. That means, so for any point of A, I say, if B is the guy that guesses whatever I have, I will assign to it the start of the other invariant, and that I will guess by the product. Okay? It seems convoluted, but it really just means use first this cardinal invariant and then use the other one. Okay? So the evaluation of that is just maximum, but there doesn't seem to be any reasonable way of assigning Borel structure to this sequential composition. Yet they are useful cardinal invariants. I want to give you I thought, a cute example. So let's think of P omega mod fin, but not as a Boolean algebra, but just as a partially ordered set. Okay? So now I want to look at maximal subtrees, for me subtrees grow down, of this partially ordered set. So that's a thing where if I restrict the relation to that subset, it's a tree. So that means it does not contain things which look like diamonds, right? But it's maximal. If I try to add one more element, it's already not going to be a tree. And it was a question of Donald Monk, from his new book, whether every maximal tree actually has to have size continuum. Well, it turns out it doesn't. Particularly in the Sachs model, one can prove that there is a maximal tree in P omega mod phi of size omega 1. Again, as I said, you could do it directly, constructing such a tree using CH or diamond in the ground model, and make sure that your tree will be indestructible by all countable length iteration of Sachs, and then use reflection to show that it's actually indestructible by the whole iteration of Sachs forcing. Or you can just use the fact that these diamonds all hold in the Sachs model and use this diamond to construct a tree. And there is just a peculiar question that Jörg Brendel was visiting me for 3 months. We spent most of the 3 months thinking about this question and we couldn't solve it. So it seems weird. It should be simple, but I think it's a very nice problem. So is D, the dominating number, a lower bound on the minimal size of a maximal tree in P omega mod phi? So there are a few more little changes that could be made to the definition to make it more general. And well, the first advantage of this Aleph 1 definable that I introduced is that I can all of a sudden talk about omega 1 because I'm not restricted by Borel, right? So a very important invariant in my sense is omega 1 equal. So I'm just guessing ordinals, okay? And it turns out that this is the strongest of all these weak guessing principles. Because of this Gallo-Atuki, it sits on top of everything. So if you have this strongest weak diamond, all right, and you can also tag along a stationary set if you want to. For that, we have only one application, but it's possible and maybe potentially useful. And so this is really the strongest of the diamonds. So if you have a cardinal invariant which is small, and you have the strongest weak diamond, then you have actually the diamond of the cardinal invariant, of the invariant. And again, this is this diamond in the presence of CH is just equivalent to the usual diamond. But it can be separated from CH. So you can sort of take CH and take diamond away from it. So of course this is nothing new. The club principle has the same property. But I believe that this guy actually carries a lot more strength of the original diamond than the club principle does. So I guess that sort of we optimize this theorem that we have with Mirna and Justin, that in fact this strongest weak diamond holds in all these canonical models. Okay. And in particular, well, I guess this is just a small corollary to this, Sachs model is provably optimal. So in Sachs model, all of these weak diamonds which can hold with the negation of CH actually hold. Okay. And this just brought me to a thought. Well, there are many things that we can prove about these models without looking at the particular forcing that it involves. So we just call a model canonical if it is done as an omega 2 stage iteration of some definable forcing which is proper and has this weak homogeneity property. And in all of these canonical models, well, we can prove many things without knowing the particularities. For instance, all small Whitehead groups are free. Well, because of the standard uniformization, well, whatever. I don't want to get into the details. I gave you the hint why Baumgartner's theorem fails in all of these models. Why you cannot separate these complicated cardinal invariants in any of these models, right? You can't prove B less than A in any of these canonical models.
Where the S sub omega is the same as the S super omega was?
It's a different one, but it's S omega is what's also called Aleph naught S. So it's the one where you just want to split countably many things at the same time. Yeah. But again, different only potentially. Yeah. And so the Malikhin's problem has I guess positive solution, because that's how Malikhin phrased it. There are these Cohen indestructible mat families. You have always these compact sequential spaces of sequential order 2. Again, you have answers to this Arkhangelsky's question. I guess one more example is this. You always have a strange CCC notion, which doesn't either Cohen or random reals. But what was surprising to me, that there are two things that I didn't see how to deduce from that, and that's p-points and Suslin trees. So just I think is a curious question whether it of course should be the case that you cannot use canonical models to solve the p-point problem or to kill all Suslin trees, but I don't see an argument. So I think these are interesting questions. And the first question here is actually very much interesting to me. So most of the cardinal invariants that we are interested in are sigma directed, like B. So that if you have in this picture, if you take countably many things here, there will actually be one guy on top of all of those. Entonces, for those sigma directed, this is actually the strongest of the sigma directed ones, just like this one is the strongest of all of them. And I would like to know whether they are consistently different. So I think that's where I'll end, and I'll leave you time for questions.
You mentioned with the Yakovlev spaces,
Uh-huh.
are they all scattered, like by definition, or are the only examples of scattered?
Yakovlev spaces are scattered by definition, but I didn't give a definition of Yakovlev spaces.
Okay,
So
right.
I can do it if you want me to, but there is an eraser. I guess I can. I still have some time at my disposal. So a space is Yakovlev if it can be seen as a one-point compactification of the following picture. So we have this special point, infinity, that we won't talk about. And now you have these countably many levels, Ln. And what you want, well, of course, on the first level, all points, all neighborhoods will be isolated. And every point on one of these levels will have a compact neighborhood, in what I've had so far, looking down, using only the lower levels. Right? So on the first level, well, I will have some almost disjoint family and sequences converging to that. And on the next level, I will have perhaps something more complicated, right? But I have the following sort of countable compactness-like property, that if I take any sequence on any of these levels, there will be somebody in the later levels whose neighborhood will intersect that set in an infinite set. And that's the thing. So these blobs looking down will be the compact neighborhoods of each point, and it gives you a locally compact topological space whose one-point compactification is the counterexample to this problem of Arkhangelsky. So this is a Yakovlev space. So now what did you want to ask about those?
I was curious whether there would are perfect counterexamples to that problem. Or
To the Arkhangelsky's problem, I don't know.
What's the
the
question?
problem is Arkhangelsky's problem.
Whether Arkhangelsky's problem has other types of examples than scattered ones.
Not that I know.
Uh-huh. Yes?
Is there a chance for formal definition of, I understand the notion of canonical model is a kind of intuitive or vague. There is no,
Oh, I gave a definition. Sorry, let me return to it. So for this talk, a canonical model is a model where you take a definable proper forcing, the same definition, you iterate forcing with the same definition omega too many times. And for the theorems that I need to hold, I need that I can steal. If I look at the generic real, I can steal one bit, put it in my pocket, and what I have left is still the same forcing. Because actually, well, maybe I can tell you roughly how the proof of this theorem actually goes. It's not a preservation theorem, because what we do is, so we look at this countable support iteration. We first go far enough so that we trap our coloring. It's definable, so we will know it forever in the later stages. So we trap all the parameters. And now we look at the following omega 1 bit of piece of this iteration. Now we steal one bit from each one of the generic reals and put it in our pocket. And what we have left is still the same iteration. But now I have a tree in my hand, actually, a tree of these sort of iterations of these initial bits. Well, it's a tree which actually turns out to be proper forcing. And because it's proper forcing, it does not add reals. So it's my poor version of a sigma closed forcing. So I can put that guy at the end and force with it. And it turns out that it's sort of sigma closed enough that it gives me the diamond sequence for the function that I trapped at the beginning. So this bit about this homogeneity is just what I need is if I steal one bit from each of the generic reals, what I have is still the same iteration.
no, what I was worried about, I've seen this definition that are sufficiently definable. So you want to freeze it like Suslin or?
Yeah, I would say Suslin to be safe. I haven't tried to optimize that part, yeah.
More if you want. Of the examples we are thinking about. There's a question with the anti-chains, right? Usually the definition of Suslin.
Suslin means that also the anti-chain
Yeah, the
relation is
relation
analytic.
excludes an anti-chain. Suslin was defined specially for CCC.
Yeah.
But you don't want that. You want
Yeah, well,
one
okay.
for proper, so you probably want pi 1 1.
I would have to think about it, what the real Borel is definitely enough.
You need probably some absoluteness of its properness and
Exactly, yes. Yeah, so you need, I really didn't want to get into that. You need sort of that its definition is sufficiently absolute that it doesn't change from model to model. The interpretation is given. That's all I need.
More questions?
And well, actually, I have one more question. I think it may be interesting. I haven't really thought about it terribly much, but I think it would be interesting to see what happens beyond omega 1, because there is an obvious way of generalizing it to colorings of higher trees than trees of height omega 1. And there are some obstacles when one wants to do cardinal invariants on uncountable cardinals. And I somehow suspect that these obstacles may have to do with sort of a combinatorics of these weak diamonds on higher cardinals, but that's just sort of a hunch and a project for future investigations. I'm done.
Well, thank you very much. That's the end of this afternoon.